All right, ladies and gentlemen, this class recording has started. So, last week, this picture up on the board, we developed this picture, and we talked about that all of these spaces that we've drawn up here represent orbitals. What was our definition of an orbital?
A place where it's probable that electrons can be.
A place where it's probable where electrons could be, right? Technically, they could exist anywhere, but there are certain places that are statistically more likely, and those are orbitals. And towards the end of last week, we started getting into doing some of this, right? Where if we have an electron in one of those orbitals, how do we distinguish that electron from the other electrons and the other spaces where electrons could be? This list over here, right? This stuff right here, we referred to them as quantum numbers. And quantum numbers are basically like an address, right? Describing a space around the nucleus where electrons could exist or are likely to exist. Now, what we're going to get into today is these quantum numbers, an address describing a space, are like an address on a house. It describes a space. The house has an address whether people are there or not, right? But there are certain houses that people are more likely to live in than other houses, depending on their location, cost, things like that. What we find out is that there are certain orbitals that electrons are more likely to be in than other orbitals based on the two factors that we've used to sort of guide us in this discussion. What did we say were the two things that really guided us into where electrons end up around a nucleus? There are two factors. What are the two factors that we deal with? What are the two things that sort of guide where these electrons can go? Because what do all electrons do to each other? They repel, but they are also attracted to the nucleus, right? They repel each other, but they're attracted to the nucleus. That combination went into determining what all these shapes were, but it also goes into determining where electrons are most likely to be within that shape setup. All right? So that takes us then to this. I realize that it's just a boring white background with black writing, but really this is just a guide for today. There's really not a lot of notes. It's more a lot of practice. Okay? So, the off-bow principle guides what we do with filling orbitals. All of those orbitals exist whether electrons are there or not. But where the electrons actually go is determined by off-bow principle. Off-bow principle states that orbitals are filled from lowest energy to highest energy. This is a theme that is going to run basically through this course. Lower energy to higher energy. Back in Unit 2, we talked about potential energy, specifically what kind of potential energy? Gravitational. Does this ball have gravitational potential energy? Yes, right? If I let it go, what happens to its gravitational potential energy? It decreases. We will find that that happens often in nature, that objects will tend towards situations where they have lower potential energy. This is gravitational potential energy. If I let it go, the ball falls. Yes, gravity pulls it downward, but if we talk about it from an energy standpoint, the ball has less energy lower to the ground. That's why it heads in that direction. Same thing is true with these electrons. Based on this information, hopefully you can make an educated guess about which orbitals get filled first. Based on what Bohr said and what Schrödinger said and the idea of quantization, which orbitals are going to get filled up first? One's closest to the nucleus, because those are the ones that have the lower energy. Right, so Aufbau principle basically states that electrons fill from lowest energy orbitals to highest energy orbitals. And based on the work of Bohr and Schrodinger and the idea of quantization, that means that we're going to go from close to the nucleus to farther away from the nucleus. These two charts you actually have in your outline. Both of them are telling you the same thing, just in a little different way. Okay? So, I like the one on the left better than the one on the right, and that's the one I'm going to reference more often. Both of them, along the outside left edge, state something about energy. The one on the left says increasing energy of electrons in orbitals, and it has an arrow pointing upward. The one on the right says relative energy, and it has an arrow pointing upwards. Meaning, how are we going to read this chart? From the bottom to the top. Because the lower energy orbitals start off in the bottom, the higher they go, the more energy they have. Okay? Good there? Okay. We're going to reference that often. Also, this chart will be on your test on Thursday, so you do not have to memorize it. You just have to know how to use it. All right? Somebody asked before, but yes, it will be on your test on Thursday. Okay? All right. So today, we are going to draw ourselves orbital diagrams. Orbital diagrams show the distribution of electrons within orbitals. Somebody earlier today asked, well, what are we doing here? Why, about halfway through class, why are we doing this? Remember, like I kind of mentioned earlier, these are all locations that are statistically likely that they will find electrons. But which ones actually get filled up? People are statistically likely to live in houses as opposed to other places. But which houses are actually filled up? That's what we're trying to figure out with or show with these orbital diagrams. An orbital diagram, depending on where you get it from. So I just want you to know that if you go to Honors Chem, or if you go to regular Chem, or AP Chem, or wherever you go after this class, the orbital diagrams may look a little differently, but they still show exactly the same thing. So sometimes there's circles, sometimes there's lines, sometimes there's boxes to represent individual orbitals. And then we use arrows to represent electrons. Meaning that our orbital diagrams are going to look like some combination of these circles and lines and arrows. Some of them might be full, some of them might be empty, some of them might be half full, right? But some combination is what our orbital diagrams are going to look like. Okay? Good there? All right, let's get started. So, first orbital diagram we're going to draw is the orbital diagram for hydrogen. So I'm going to go here and kill this one. Sorry, close that one. I know, I shouldn't have said that, but I know. All right. We are going to start off with hydrogen. Now, if we are drawing a diagram that shows the distribution of electrons around an atom, we have to know how many electrons we have to distribute, or distributes. So, where are we going to find out the number of electrons that each element has? Periodic table. Amanda, how many electrons does hydrogen have? How do you know that? It's its atomic number. Technically, the atomic number tells us what? Protons, but we know that that has to be the same. So, we know that for hydrogen, we have to place one electron, and that's it. We go back to our chart that you guys have on page 1 of your outline, okay, the one I showed you before, and you told me that we are going to read that chart from where to where? Bottom to top. So, you start at the bottom of the chart, and the first orbital that you come across is which one? 1s. Okay? The fact that it's labeled as 1s should tell you two things about it. What should it tell you about it? It's spherical, and where is it? Pretty close to where? Pretty close to the nucleus. It's not, Audrey, it's not the first sublevel, it's the first principal energy level, okay? Because it's the first one, okay? Then we will use a line. I usually use the line, especially when I'm doing stuff in class because it's just faster. I will use a line to represent the orbital. So this line, labeled as 1s, represents that 1s orbital. How many electrons do we have to place? Just one. And it says right above it on your outline, how do we represent electrons? Arrows. A lot of times, you will see them drawn as just with single sides on them, mostly to save time, okay? If you want to draw it as a full arrow, go for it, okay? That's perfectly fine, does not make it wrong or right, it's just, this, that's fine, no problem, okay? All right, good here, okay? This diagram, an orbital diagram, would tell us the same thing as this picture right here, right? This orbital diagram is the same thing as this picture, just a condensed version, okay? Good there? All right. But we kind of talked about on Friday, how many electrons can that orbital hold? Electrons can hold a maximum of 2 electrons. So the next orbital diagram that we're going to draw is helium. You look on your periodic table and you find out that helium has how many electrons? 2. On the chart from the first page, we learned that the first orbital that's filled is which orbital? The 1s orbital. Okay? But, like we discussed the other day, how many electrons can this orbital hold? 2. On our quantum numbers, how do we distinguish 2 electrons that are in the same orbital? There was one quantum number that's important. Spin quantum number, right? If we go back to this picture right here, right? These 2 electrons are in exactly the same orbital. And N, L, and M are exactly the same for both of them. But the S quantum number, right, we said distinguishes one from the other. One got labeled as -1/2, one got labeled as +1/2. And we only needed to have 2 values there. Just the only 2 possibilities it could be. We have to distinguish these 2 electrons that show up in this orbital. This represents 1 electron, okay? We represent the other electron with a downward arrow. Angela, go ahead. Yep. This is the 1s orbital. Okay? N is 1. L is 0 because it's an s orbital. But N is 1 because it's the first principal energy level. Where is this orbital, Angela, in relation to the nucleus? Very close, meaning that electrons in it have how much energy? Low amount of energy, right? This is the first place where we're likely to find electrons. Okay? It's the first principal energy level. It's an s orbital. It's an s sublevel, right? That's lower energy, right? This line with the 1s underneath it represents that yellow sphere. Well, the line represents the orbital. right? It doesn't tell you really anything about its shape like our other picture did, right? This is a less detailed version of the picture that we drew over the past 4 days, okay? And on Wednesday, we're going to get an even less detailed version, a more condensed version of the picture, right? Because doing this, doing this, like, let's say later on we're going to do an orbital diagram for potassium, and potassium has 19 electrons. Doing this for 19 electrons is not convenient, okay? So that's what we're doing here. We're representing the same information, just in a more condensed version. Does that make sense? Okay. We'll go with it, okay? So we got hydrogen, right? And then helium is going to look like this because that 1s orbital, the yellow sphere, can actually hold 2 electrons. And so that's representing those 2 electrons.
So if there's more than 2 electrons,
Yep. Audrey, question or are you good?
no,
Good.
So the whole S, is that, okay, this is corresponding to the whole S Q. Okay, I was
So even though we haven't drawn the s orbital as a sphere in this picture, because you know about s orbitals, that's what I said. When I said the first orbital that we fill is the 1s orbital, you should be able to tell me 2 things about it. 1, it's spherical, because it's an s orbital, and 2, it's close to the nucleus, because its principal energy level is 1. Okay? Alex, is that good? Okay. Okay. Angela, go ahead.
So if it was in a pedal,
Hold on.
okay, cool.
Chill out. We'll get there. All right. This idea of the 2 electrons comes from what we refer to as the Pauli exclusion principle. Just like on Friday, we talked about each orbital can only contain 2 electrons. These electrons have to be distinguished from one another, and we do that by saying that they have opposite spin. Notice, opposite spin is in quotation marks. It doesn't literally mean that they spin in opposite directions, or that they go around the nucleus in opposite directions from one another. It's a mathematical way of distinguishing one from the other, okay? What that means, when we draw them on the orbital diagram, one arrow goes up, and the other arrow points down. That's how we tell one electron from the other, okay? All right, good there? Okay. The next orbital diagram that I have you listed on your outline is for lithium. And you go on your periodic table and you find out that lithium has how many electrons? 3. The whole number. So, the first orbital that always gets filled in every atom is which orbital? S. Specifically, which S? 1s. So we draw a line, we label it as 1s. How many electrons fit in that orbital? 2. 1 arrow up, 1 arrow down. But we still have one electron that we have to place. So we go back to our chart, right? Reading it from bottom to top. What's the next orbital that we come across? 2s. Oh. So line, and we label that one as 2s. Okay? How many electrons does that orbital have in it?
1.
Just 1. Okay? What does that correspond to on our drawing that we made the past couple of days? No. Red sphere, right? It's the second sphere. It's the red sphere. Okay? Good there. Okay. Skipping one, the next one that's on your outline is boron. You go to your periodic table. How many electrons? 5. Because that's boron's atomic number. Okay? The first orbital that gets filled in every atom is? Okay. 1s. How many electrons can it hold? Okay. The next orbital from the bottom is the 2s. Line 2s. How many electrons can it hold? 2. So that's electron 3, that's electron 4. Okay? All right. Now you go to your drawing, what's the next set of orbitals that we come across? 2p. All right? So let's go here, let's go here, let's go here. Okay. Now, 2p is the next one up from the bottom, meaning that it has the next lowest energy after 2s. However, how many p orbitals are there? 3. Remember? Left, right, up, down, front, back. X, Y, Z. Right? Together, they make the p sublevel, but there are 3 individual orbitals. Notice, here on your drawing, how many lines are there next to 2p? There are 3 lines, representing the 3p orbitals that exist in the second energy level. No, these next to it. Dash, dash, dash next to 2p. Each one of those lines represents a single orbital. So there are 3 individual 2p orbitals. The fact that they are p orbitals tells you what about them? They are petal shaped, right? When I draw this, okay, that represents one of the red petals on our drawing. However, we said that that diagram gets filled from bottom to top. What do you see about those 3 lines? Are any one of the 3 closer to the bottom than the other 2? They are not. Meaning, there is no advantage to an electron being in the xp orbital versus the yp orbital versus the zp orbital. One is not favored over the other 2. Moral of the story, when we encounter a sublevel that has multiple orbitals, we draw all 3 of them. Because they are all exactly the same. Remember, it would be like building 3 houses on the same street in the same city. The 3 houses are all exactly the same. Same floor plan, same carpet color, same number of bedrooms, same appliances, exactly the same. Okay? They even face the same woods. You have the same view. Okay? We have one electron left to place out of boron. If he's the first electron to move in on the street, does it matter which house that he moves into? They're all exactly the same. It doesn't matter. Usually, we will see that one single electron written just in the one that's the farthest to the left. Not that that represents the X or the Y or the Z, it's just where we usually write it. Okay? Good there. Okay, now, next up is carbon. Carbon has an atomic number of, has an atomic mass of 12, has an atomic number of 6. Okay? Meaning, we have to place 6 electrons. First place electrons go, which orbital? 1s. 2 electrons there. Next, 2s. 2 electrons there. 4 down, 2 to go. The next one that we come across, 2p. But okay, so we said same house, same street, same floor plan, same color scheme. Electron number 5 moves in here. Okay? Now, electron number 5 is a family that has 2 kids. All right? That's a 4-bedroom house. So the parents use 1 bedroom, each of the kids uses another bedroom, there's 1 bedroom left, right? There's still another electron. Even though there are bedrooms left in this house, is that electron going to move into the same house that already have people living in it? No. Okay? Does it matter where this 6th electron goes? Yes. It can't go here. Those other 2 houses are exactly the same, but it's not going to move into a house that already has people in it. All right? Angela, go ahead.
So, you can't have 2 arrows in any one.
You can't have 2 arrows in any one orbital until all of them have at least 1 arrow. Okay?
Oh, I get it.
Okay? So, we call this idea Hund's rule. Okay? Hund's rule says electrons will not pair up within orbitals until each orbital within a sublevel contains at least 1 electron. You guys have that written word for word on there, right? Underneath the carpet? Okay. Electrons distribute themselves evenly as much as they can. Okay? Does that make sense? Yeah. All right. Now, you don't have to draw this, but just to look at that idea a little further. Okay? If we go with nitrogen, okay? Nitrogen isn't on your outline, okay? But nitrogen has 7 electrons. Okay? Yes? You good with that? Okay. Where's the 7th electron going to go? Okay. It's going to go here. All right. Well, you do because this one has more electrons, right? Lithium, lithium only goes up to the 2s level, right? Yeah, there's only 1 electron there, right? Okay. Okay, so boron has only how many electrons? So it only has 5 arrows, right? All of those orbitals are still there. There's just nothing in those orbitals. But now we start putting things in those orbitals, right? Okay? All right, now though, if we go to oxygen that has 8 electrons, okay, there are still room in these orbitals, right? They can each hold 2, right? So now they'll start pairing up. Does it matter where we draw that 2nd arrow? Doesn't matter where we draw that 2nd arrow. The 8th arrow. It doesn't matter where we draw the 8th arrow as long as it's upside down. Okay? Yeah, sure, okay, there we go. Right? Grandma moved in, right? Same house, right? It still's got room, so another electron moves in there. Okay? Or maybe they have another kid. Right? Or, wow. What? Sure. Well, then they would go down. The number of arrows would go down, right? I mean, we don't want that. That's not till chapter 5 or chapter 6 when we get into bonding. So, all right. Okay, so let's do this. All right. Right, but I want to make a point about it for a second. Okay. All right. So the last one on the sheet, right, the last one on that side is neon. Okay. Got its bottom. Yes. Now, I think most of you got the picture and you jumped ahead, which is fine, okay? But I want to make a point with this, okay? So, we have to place 10 electrons. Now, If I gave you neon on the test, I wouldn't be able to necessarily tell if you did it this way. But the first orbital that has to get filled up is the 1s orbital, right? It can hold 2 electrons. The second orbital that needs to get filled up is the 2s orbital. It holds electrons 3 and 4. Next, (2p), right? Now, this is the part. If you turned it into the test, I would not be able to tell whether you did it this way or not. But if we did it according to Hund's rule, right, it would go 5, 6, 7, 8, 9, 10. You don't necessarily have to fill them in that way because the final result, I wouldn't be able to tell whether you went 1, 2, or 4, 5, or 6, 7, 5, 6, 7, 8, 9, 10, right? Okay. But that's how it would order would go. Okay? Good there. All right. We're going to jump ahead a little bit. We are going to jump ahead to potassium. Okay. All right, so you find potassium on the periodic table. Okay, potassium has 19 electrons. All right, so we use our chart. First orbital to get filled, 1s. 1, 2. Next orbital to get filled, 2s. 3, 4. Next, 2p. 5, 6, 7, 8, 9, 10. All right. What's the next one up? 3s. How many electrons can 3s hold? Only 2. 11, 12. Next one, 3p. How many 3p or orbitals are there? Only 3. Okay. So, 13, 14, 15, 16, 17, 18. Okay. Why do you think I picked this one? All right. Then the next one that shows up is 4s. Okay. Now, all right. Going in order, right? We talked about the other day that 3p is followed by 3d. But what we find out is that 4s is actually a lower energy than 3d. So even though we haven't filled the butterfly-shaped orbitals in the third level yet, we jump up to the spherical orbital in the fourth level, because that's what the chart says.
The chart.
I gave you the chart.
Yeah. So the chart's right.
Yes.
Not me.
All right. Last one. Okay. Not magnesium. Manganese. Okay. So manganese has 25 electrons. All right. Hey, let me get this done real quick. So 1s, 2s, 2p, 3s, 3p, 4s, but then the next one up after 4s is 3d. How many d orbitals are there? 5. 1, 2, 3, 4, 5. You got to write all of them. Okay? So now we have to fill how many electrons? 25. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Wait, hold on. How many do we have left? 5. How many 3D orbitals are there? How do they get distributed? 1 in each. All right. 1, 2, 3, 24, 25. Okay. This is on the test. All right. So real quick, in my hand right here is your homework for tonight. You only have to do questions 1 through 7. Answers are posted on the calendar.